Hello, today we'll be doing a 2008 AP Physics C response from the Electricity and Magnetism section. We're working on number 1. The question reads, a metal sphere of radius A contains a charge positive Q and is surrounded by an uncharged concentric metallic shell of inner radius B and outer radius C, as shown above. Explain all algebraic answers in terms of the given quantities and fundamental constants. Part A says, determine the induced charge on each of the following and explain your reasoning in each case. 1. The inner surface of the metallic shell. So first of all, there are some things we need to realize. This is a conducting shell. So inside, the charge is going to be 0. Overall, this conducting shell has a charge of 0 as well. So the outside charge and the inside charge will have to cancel out. Because this shell is experiencing a charge from the inner sphere, through Gaussian surfaces we realize that the inner charge is in fact equal to negative Q and the outer charge is equal to Q, which will make sure that the shell is neutral as well as having a charge of 0 inside. Moving on to part B, determine expressions for the magnitude of the electric field E as a function of R, the distance from the center of the inner sphere in each of the following regions. Electric field E is equal to KQ over R squared. In this case, K, is always a fundamental constant, Q is positive Q, and R squared is going to vary depending on the question part. Part B1, R is less than A. Inside of here, we are inside of a conductor, and all good conductors have an internal charge of 0. And an internal field of 0 as well, so this part is easy, it's simply equal to 0. Part 2 asks for R in this region, which is not inside of conductor, so we go to this formula. The only charge is Q, so it is KQ over R squared with the R somewhere in this range. Part 3 asks for the electric field when R is in this region. Once again, we are in a conducting object, and inside of that, the electric field is equal to 0. So this will be Q0. This we found was KQ over R squared. And then for part D, we are in C anywhere out here. This is not inside of a conductor, so we just go back to this formula, and it is KQ over R squared. This question is that simple. Part C, on the axis below, sketch a graph of E as a function of R. So basically everything we found in part B, we just need to sketch a graph of it. 0 to A was equal to 0. The electric field is 0 in that area. From A to B, the electric field is gradually decreasing because KQ over R squared is equal to E. So the bigger R gets, the smaller E gets. It's inversely proportional. Therefore, R gradually decreases and it's concave up because it is 1 over R squared, essentially. And then B to C, we're once again inside of a conductor, so this is 0 again. And then from C onto basically infinity, the charge is going to be going concave down as it will eventually become asymptotic to 0. Part D, an electron of mass m, E, carrying a charge negative E is released from rest at a very large distance from the spheres. Derive an expression for the speed of the particle at a distance 10r from the center of the spheres. We go back to our work energy formula. Energy is either going to heat you up, move you, or heat you up, speed you up, or change your potential. So 1/2, we know there's no internal energy in this situation, so 1/2 mv squared minus kq over r is equal to 0. This is the basic formula. Because the initial potential energy is equal to kq over r, and then the final kinetic energy is 1/2 mv squared. And when you do the final potential is going to equal 0, and the initial kinetic is 0, so you do get this equation. You set them equal to each other. Here we plug in Q for one of the charges, and negative E, an electron, for the second charge, which is just given in the problem. And then we multiply by 2 and we make the R 10 and we divide by mass. So it's basically just algebra and we get this. And that is the answer. V is equal to the square root of KQE over 5RM. Thank you.